Hello everyone, welcome back. In the last couple of classes, we looked at different discretization approaches, especially the spatial discretization, where we saw how to basically use the two-sided formulation and one-sided formulation to get basically approximate of a derivative using the numerical approach for a given grid. We also looked at the compact schemes, which basically gives you a higher order of accuracy for the same stencil. Now, it is time to use those discretization schemes to solve some problems. So, of course, the problem that you want to solve is the Navier-Stokes equations, right. So, these are the equations that govern the fluid flows, but Navier-Stokes equations are complicated. So, before we basically dive into the full fledged Navier-Stokes equations, we need to look at simple equations which we call as the model equations and try to solve them using the discretization approaches, because these simple equations give you a lot of insights about the behavior of these numerical schemes. So, let us start the class then. So, before going there, let us say that we want to solve the Navier-Stokes equation. So, what are the terms that we have in the Navier-Stokes equations? So, let us take very simple one dimensional Navier-Stokes equations and incompressible. So, let us simplify the Navier-Stokes equation as much as we can, right. So, we can write this del u by del t plus u del u by del x is equal to minus 1 by rho del p by del x and plus nu del square u by del x square, right. And let us ignore any body term that may be present, right. From our knowledge that we gained in the last few classes, we know that this is a temporal term, this is the convection term which represents the hyperbolicity in the equation, this is the diffusion term which represents the ellipticity in the equation, and in different limits of the Mach number and the Reynolds number, these equations may be more close to an elliptic equation or an hyperbolic equation. And because of the presence of this time term, it is also a parabolic equation. So, you can write it maybe in a conservation form, that will be u y square by 2 plus p by rho will be nu delta u by del x square, right. Now, this also like this is only the momentum equation, you may have the you must have the mass conservation and you may have the energy conservation also, especially in the compressible flows. So, if you try to solve it, you have 2-3 variables at least. In this case, you have u and p in the one dimensional case, and if it is compressible, then you will have rho also and t also. So, before showing this solving this problem which has got 2 variables to solve, we will look at simple problems. So, let us start taking breaking these equations into simple equations. Let us have equation which is del u by del t plus u del u by del x, and let us put all other terms on the right hand side as 0, right. So, this equation is called the non-linear convection equation. Why it is non-linear? So, of course, we have discussed properties of the equation, but one very simple way to look into whether the equation is linear or non-linear is that let us say this has got 2 solutions, this equation has got 2 solutions, one is u 1 and other is u 2. If you add these 2 solutions, they individually satisfy this equation, and if you add them up, that should if they also satisfy this equation, then it is a linear equation. So, let us say this u 1 has got it satisfies the equation. So, del u 1 by del t plus u 1 del u 1 by del x equal to 0 and del u 2 by del t plus u 2 del u 2 by del x equal to 0, right. So, these are the 2 solutions for this equation, and if you add them up, let us say you do a plus b, and if that also satisfies this equation, then it is a linear, otherwise it is a non-linear equation. So, if you do that, this is del by del t u 1 plus u 2 plus u 1 del u 1 by del x plus u 2 del u 2 by del x, right. So, it does not satisfy, right, it does not satisfy this equation. So, that is why it is not a linear, it is a non-linear equation. Okay. Let us simplify it further. Okay. Write a equation which is del u by del t and keep the convection speed as constant. So, C is a constant. Okay. And if this has got two solution u 1 and u 2, okay, you can quickly see that this thing will transform. So, this will become C del u by del x and C del u 2 by del x, and then you can write it as C del by del x u 1 plus u 2, right. So, when u 1 satisfies the this equation and u 2 also satisfy this equation, and the linear combination of both the solution also satisfy this equation, then these equations are basically the, so this will become a linear equation, right. So, before even looking into this non-linear equation, we will look into this linear convection equation. So, this is a linear convection equation. We have also seen earlier that it represents a wave equation. Okay. So, you can also write it delta u by delta square is equal to C square delta u by del x square. All you need to do is like you write del u by del t equal to minus C del u by del x, and then you double differentiate it and substitute basically interchange the del by del t and del by del x term, and you will get this equation. This is the wave equation. Other term that we need to worry about in this is the diffusion term. So, let us look at that also separately. Okay. So, if you look that also separately, so how will that look like? Okay. So, we will have del u by del t is equal to nu del t u by del x square. I am ignoring the convection term. So, first we considered the convection term and then we are considering the diffusion term. Okay. What kind of equation this is? So, this is an parabolic equation. So, this is parabolic in time and elliptic in space, right. So, we will look at also this equation separately, okay, and we will see what role this nu plays in solving these equations. Okay. And once we have done that, so this is linear convection equation, this is called the diffusion equation. Okay. So, once we are done with the testing our schemes for the convection and diffusion, then we will go something called convection diffusion equation, simple convection diffusion equation. Okay. So, what will that have? So, first we will have the linear part which is del u by del t plus C del u by del x is equal to nu del 2 u by del x square. You can see that slowly you are going towards our Navier-Stokes equations that you want to solve, right. So, this is linear convection diffusion equation, and then we will go to non-linear convection diffusion equation, okay, non-linear CD equation, that is also called as the Burger's equation. Okay. So, that equation will look like del u by del t plus u del u by del x is equal to nu del 2 u by del x square. So, once we are good and we see that our numerical schemes and our discretization schemes are working fine with all these different kind of equations, we will have confidence that now we are ready to tackle the full Navier-Stokes equations, first in 1D, then 2D and 3D. Okay. But there is a lot of things that we need to learn and find out that it is not only the accuracy, but the stability of the scheme. Okay. Some schemes may be stable for certain problems, some schemes may not be stable, and even if it is stable, whether it is conditionally stable, that means it is stable under certain constants like the limited delta t value or delta x value or the value of the convection speed, or it is unconditionally stable in the sense that regardless of what is the value of you are using, it is going to give you a solution. Okay. Then lastly, you have to worry about the convergence, whether the solution is converging or not, whether the errors that you have in the beginning, because any problem that you will start will have certain initial condition. okay, and then finally, it has to go to the solution that we desire. So, how fast it is going to the solution, right? Is there any thing that is stopping it to go to towards that solution? Okay, so, those are the things that we need to worry about. Okay, so, let us start one by one. So, first we will start with the convection equation. Okay. So, this is the linear convection equation that we have been discussing. Remember, c is a constant, it is a constant wave speed, okay. And if you discretize it, okay, so del u by del t, use a forward differentiating, okay. So, this will be u n plus 1 minus u n by delta t, right. So, we are discussing everything in 1D today, okay. So, this is your x and this is your t, okay. So, you have discretized it everywhere. So, let us say this is I plus 1, I minus 1, okay, I plus 2, I minus 2, and this is n, and then you go to n plus 1, okay, n may be 1 here, and then it goes to next step, and then you go to next step. Okay. So, everything is known at this n, okay, which is let us say n equal to 1. So, everything is known. So, you know what is u I at 1 everywhere. Okay. So, this is u I at n equal to 1. So, I will use consistently for the subscript denotes the spatial discretization and superscript denotes the temporal discretization. If it is 2D, it will become let us say u I comma j n. Okay. So, here if you write it at I, okay, this will become u I n and n plus 1 minus u I n by delta t, right. And what is the order of accuracy? Similar to what how we did in the one sided formulation scheme, okay, for the spatial, there we it was the first order scheme. So, similarly, the order of this will be delta t, right. This is in time, and del u by del x. Okay. So, you can use the forward differentiating, backward differentiating, center differentiating, whatever you want, but you will see that depending on what scheme you use, our solutions may be correct, incorrect, or solution may blow up also. Okay. So, if you do it at I, that will become u, I am using this. So, this I have used the forward in time, okay, f t, forward differentiating time, and backward differentiating space, okay, b s. Okay. This is scheme is called f t b s, forward in time, backward in space. Okay. So, this is u I n u I minus 1 n by delta x, okay, and this will become order of delta x, right. So, if you write approximate this equation del u by del t plus c del u by del x, this will become u I n plus 1 minus u I n by delta t plus c u I n minus u I minus 1 n by delta x plus order delta t delta x. This is your order of accuracy. So, it is first order in time and first order in space, right. So, you can approximate it, and this is the equation that will become, because the value is 0 on the right hand side, okay. And you can rearrange it here. So, if you put this equal to 0, okay, approximation. So, that will become 0, and then you can write it, you can rearrange it. So, this will become u I n plus 1 will be u I n, and then you take on the right hand side. So, that will become negative minus c delta t by del x, okay, u I n minus u I minus 1 n. Okay. So, why I wrote in this form? Okay, because you want to go to the n plus 1. So, right hand side everything is at n. So, you know the value at n, and then you have discretized your function at time n at every point, okay, I equal to 1 to I equal to capital N, okay, and you want to see what happens to n plus 1, right. And how do you go to n plus 1? So, this n plus 1, the distance is delta t, okay. We are going step by step. You might want to go to a maximum time, let us say t max may be very different, t max may be let us say 100 seconds, but delta t may be very very small, maybe 0.01 second, okay, because we will see, okay, why we cannot jump so big. So, here very important thing that you will note is this number, this is called Courant number C delta T by del x, okay, and we will write this number using a special symbol which is lambda, okay, minus lambda u I n minus u I minus 1 n, okay. And this number has got very big significance in CFD. So, regardless of what kind of problem you are solving using Rance approach, LES, DNS, whatever problem you are solving, you need to always take care of this number which is the Courant number. It is also called the CFL number. I mean very crudely if you see what it represents. So, C delta T, so C is the convection speed and delta T is your time. So, this unit will be meter per second into second some meter, okay, and delta x is basically your grid distance, that also is meter. So, basically it says that how much the information is travelling, okay, with your convection speed, okay, and whether that distance that is travelling. So, the distance is travelling is C delta T, right, for a given delta T at a convection speed as C, right, and delta x is basically your grid distance. So, let us say this is your delta x, okay, and your C delta T would be, let us say I say that my C delta T is this. So, if the C delta T is greater than delta x, that means your information has basically jumped over the grid, okay. So, it is not smaller than your grid size. So, you can see that the information propagation is not proper in this particular case. So, that is why the solution will blow up in most cases, okay, unless we go to the implicit scheme which I will introduce later, okay. But typically if you are just using a explicit approach like we are doing here, okay, and we see that my C delta T is greater than delta x, then the information propagation is not proper, okay, you are jumping over the grids and the solution will likely to be blow up, okay. So, let us try solving this equation. So, you can basically write a very simple code, okay. So, before we solve we need some initial condition and some boundary condition, okay, that is for whether you are solving analytically or numerically, this information is required. So, in this particular case we start with a very simple jump condition, okay, or you can say that this is a square wave, okay. So, my initial condition is u equal to 2, okay, between 0.5 to 1, okay. So, the blue line here basically shows your initial condition. So, it is 1 everywhere, okay, and then it is 2 between 0.5 and 1, okay. So, this is my initial condition and I want to see the propagation of this wave, okay, due to the linear convection, okay, that is our purpose. So, if we have a linear convection equation del u by t plus C del u by del x equal to 0 and our initial condition is given, okay, u x comma 0 is basically our square wave which is basically it is 2 if it is 0.5 to 1 or it is 1, okay, for all other stages. So, this is my initial condition. So, this is the wave that we want to study, what happens to this wave as it convects, okay, under the constant convection speed of C. We also need to set up the boundary condition because you as you have discussed that at this end and this end, okay, we need the boundary condition. You can use a periodic boundary condition for example, where it is basically circulating or in here what we are doing, you are using this value as 1, okay. So, it goes there and it becomes because it starts from 1 and goes to 2. So, we will propagate in a way that our total distance of the convection is lesser than this distance, okay, else we have to use a periodic boundary condition. What periodic does is basically if let us say the wave forms like this and then it will start the same thing, same distance from there, okay. So, that is a periodic boundary condition. We will have discussion on periodic boundary conditions later, okay. So, let us say if I set my convection speed as C equal to 0.5, right, my convection. So, my wave is convecting at the speed of 0.5 and we want to see what happens as 0.5 second, okay. This is let us say meter per second and this is 0.5 second. So, what will happen, our convection speed is positive, C is a positive number. So, this wave will travel on the right side, right, and what is the distance that will travel, that will become C t. So, this is 0.5 into 0.5, that is basically 0.25, right. So, it will travel 0.25 distance, okay, which is what you are seeing, and your final condition would be basically going from here to here, and you can see that it maintains the shape, there is no change in the shape. So, this is your final time, t equal to 0.5 second, and this is your t equal to 0 second, okay, in the beginning, right. So, there is no diffusion here, the reason that it maintains the shape. Okay. So, this basically it will be overlapping here. Okay. So, it maintains the shape. So, I have shown you the initial condition and the final condition. Let us see how what are the intermediate conditions and what are the schemes that you are using, what are the parameters that you are using for the solution. So, you can actually go back and quickly write a simple MATLAB code. Okay. For example, this what you see here is this is my initial condition, we have defined our wave, and this is the same expression, this is a pseudo code for solving this equation, right. This is u I n, okay, c delta t by del x, and dt and dx you can fix. So, let us say you know what is your x max, okay. Let us say you take the x max as 2. So, your problem is like this, this is 0, 0.5, 1 and 2. So, your x max is 2 and your t max, let us say you want to go to up to 0.5 second, right. So, this is your let us say 2 meter 0.5 second, and you can fix your convection speed, let us say you fix the convection speed as 0.5 meter per second, right. So, you want to see that under the linear convection what is happening to this for different parameters of for example, you can change your delta t which is dt here, you can change your delta x, okay, and you can see how the things are changing. You can also change your convection speed and see what is happening. So, this is a simple pseudo code you can go back and write, and as you can see here this is a backward differencing, I am doing I minus 1. Okay. This is a very simple code to write, okay. Please go back and write it, and I am showing you some solution. Okay. So, here you can see I have taken this convection speed as 0.5, your grid size is 0.002, okay, dx, and your time is 0.0033. So, your time discretization delta t is much smaller than the delta x, and if you calculate the lambda which will be basically c delta t by delta x, so the value comes to be around 0.825. Okay. And I am using this forward in time and backward in space scheme that we have discussed, and this is how the solution behaves. So, this curve that you see, this one is your time equal to 0, right, and because we are using a very small time step, remember the delta t is 0.0033. So, I am plotting it every like 50 time steps, okay, no, so every 30. So, this is dt equal to 0.0033 and multiply by 30, that will give you 0.1. Okay. So, I am not this is not like every time step, but every 30th time step I am showing the plot, right. You can see that and the grid size, as you can see, it is very fine, your this is 0.002. So, if your x max is equal to 2, so I am using n x equal to 1001, right. It is a very fine grid. Okay. So, you can see that now it is propagating, and there are certain effects that you can see, okay, if you look at very closely. So, you had very sharp corner here, okay, in the beginning, but as it went on the right, you can see that the sharp corner has slightly become more diffused, right. So, despite having no diffusion in the scheme, so there is no new term, okay, there is no new delta u by del x square term, still you have having some diffusion, you can see at these corners also. That means, our scheme itself has got some certain diffusion, okay, that is what is called the numerical diffusion. Okay, and we have to basically estimate what is the numerical diffusion in your equation. That is a very important parameter, especially if you are going for a high accuracy simulation. Okay, let us say LES and DNS. If you are using a very dissipative scheme, very diffusive scheme, then it is likely that you will not get the very accurate solution. Okay, the things will be very diffused, especially let us say if you have shocks or something, then what will happen that you will have a very diffused shock. Okay, instead of a sharp discontinuity, you have the discontinuity over a very long distance, right. So, which you do not want. Okay, so, this is how the solution will look like. Okay, now let us change some parameters, okay, and we what we do, we basically make the mesh very coarse. Okay, so, we have x max equal to 2. So, we take n x is equal to I think 51, okay, only 51 grid points. Okay. So, then if you do that, okay, you will see that now also it is marching on the right. Okay, this is your t equal to 0, this is your t equal to 0.1, 0.2, 0.3, 0.4 and 0.5, right. But you can see that you have, it does not maintain that sharp shape that you have. You would expect that your solution would look like something like this, like we saw in the earlier slide. Okay. There is no diffusion. So, it should basically maintain the shape like this, but you can see that it is getting highly diffused as you basically decrease the grid size. You can see that the sharp corners are gone completely. Okay. It is no longer looking like a square wave, but it is rather looking like a sine wave, it is a continuous function, right. So, why did it happen? Because we used a very coarse mesh. Okay. Remember this lambda, which is the Courant number, is still very small. Okay. So, the coarse mesh gives you the solution which is very diffused, and that is why the grid independence test is necessary. That means, your grid is not, your solution is not changing as you refine the grid. Okay. If you get a coarse mesh, it is likely that you will get a solution, the solution may converge also, but it will not be accurate. Okay. That is the learning from this part. What is happening here? So, here what we have done, we have basically increased the convection speed. So, now my C is equal to 1 and kept my dx and dt as it was in the earlier slide. Okay. This slide. Okay. So, it was 0.825, that time the lambda was 0.825. Now, we just double the convection speed. So, my lambda has become 2 into that value, okay, whatever it was. So, now it has become 1.65. So, my Courant number exceeded 1, that means, my C delta t is now greater than delta x. I am jumping over the cells, right. So, when we did that, you can see quickly that our solution blew up. Okay. It is so, you can see these lines, basically it is going towards infinity, it is very large value. Okay. And since I have used the limit in the x and y direction, you do not see it here, but it is all everywhere. Okay. And the thing that you desire, that it is going to convect on the right side, that is not happening. Okay. So, if you are increasing your convection speed, you have to accordingly reduce your delta t, so that your C delta t is smaller than delta x, and that is what we have done here. So, earlier my delta t was 0.0033, okay, we have reduced it to 0.002 and it is just equal to 1. Okay. And then you can see that we are getting the solution, this is at different times, okay, and this is 0 and this is marching towards 1. So, this wave that you see, basically this is your initial solution, okay, this is your initial solution, and then it is marching towards the right, okay, at the convection speed, which is equal to 1 here. Let us do some more experiment. Here what we did, we changed the scheme. Okay. So, we changed it from FTBS to FTCS. So, forward in time and central in space, that means your equation become del u by del t plus C del u by del x equal to 0, and this is u n plus 1 minus u n by delta t plus C u I plus 1 n minus u I minus 1 n by delta x. Okay. And what is the order of accuracy of this? This is delta t and delta x square. Remember, this is a centrally fencing scheme, we are approximating it by centrally fencing scheme, which is the second order accurate. So, you will expect that your solution will become better, because this is a second order scheme, right. This is equal to 0. Okay. You can ignore this part. So, this is what we are solving, and if you rewrite it, this will become u I n plus 1 will become u I n minus C delta t by delta x, 2 delta x actually, okay, this will be 2 delta x, u I plus 1 n minus u I minus 1 n, and you know the value of at n everywhere, and you just do that and you solve this. You can see that you have got lot of oscillations near the discontinuity here, both on the left side and the right hand side. Okay. So, despite being more accurate, this scheme, the central scheme is not stable, right. And why it is happening, you can think of a very physical reason. Okay. So, let us say, so this is your grid and your convection is happening on the convection is positive. So, information is happening from both left and right. Okay. So, this direction is called your upwind, from where the information is coming. Let us say you are at this place, okay, you are at this place, okay, and the right one is called the downwind. Okay. So, when you want to calculate your gradient, you are taking the information from both, this is I plus 1 and this is I minus 1. So, you are taking the information from both the sides, okay, but your wave is travelling from the left side. Okay. So, you do not have the information on the right side, but you are still taking the information from the right side to calculate a gradient, and that is why it basically blows up. Okay. This is FTCS, this is not C equal to 0.5 only. Okay. So, that is why it blows up, because you are taking the information from the downwind also, where information is not travelled yet. This is basically C equal to minus 0.5, and but you are using this FTBS only, forward in time, backward in space, like we have been using earlier for C equal to 0.5, and you can see that still the solution is blowing. Okay. This is FTBS, not the central differentiating, this is the backward in space. Why it is blowing? The reason for that is, now the C is negative. So, your information is travelling from right to left. Okay. So, when it is travelling from right to left, this is your upwind and this is a downwind. So, you need to basically take the information which is on this direction. Okay. So, earlier we are using, so in FTBS what do? You do del u by del x is equal to u I minus u I minus 1 by delta x. So, if this is my I, this is my I minus 1 and this is my I plus 1, right. So, you are taking the information in this direction, right. You are taking making use of I minus 1 and I. So, if you are changing the convection speed, the information travel from right to left, you have to still obey the upwind. So, in that case you have to use this FTFS, that means the forward in space. So, that will become u I plus 1 minus u I by delta x. So, this is your FTBS and this is your FTFS. Why you have to do that? Because we have to honor the upwinding, okay, the direction of the travel of your convection. Okay. So, once you do that, so we just change that negative convection speed, but we are using this FTFS, forward in time and forward in space, and you can see that now it is travelling on the left side. Okay. So, this is your 0 solution, okay, and then it is travelling on the left side because the convection speed is negative. So, to honor the negative convection speed, we had to change our scheme. So, what we learnt here is basically our solution, basically whether we are getting the correct solution or not depends on the choice of your scheme, depends on the parameters that you choose, your grid size, your time step size, and whether that will be stable or not, that will be determined by another parameter, which is the Courant number. You will see that as you go to the implicit schemes, the Courant number may not be very important, because you can basically use a very high Courant number in that. So, there are other considerations that we need to think about. Okay. So, in the next class we will discuss about the diffusion equation and the convection diffusion equation. Okay. Thank you very much.